Welcome to section 2.6, rational functions and asymptotes. This is really quite the prelude to 2.7 where we get into full-fledged graphing of rational functions. So let's start out with what a rational function is. A rational function, after you get through reading all this, we recognize all it really is just a polynomial divided by a polynomial. And then there's a discussion of asymptotes, and we've been exposed to asymptotes before. Here we have, I'm going to brighten this up just a little bit. Here we have a definition of vertical and horizontal asymptotes. The line x equals a, so that's a vertical line, is a vertical asymptote, and graphs like to come in and touch, or not touch, but approach vertical asymptotes. So if I had something like, let's just say I have y equals 1 on x minus 2. Quickly we recognize that 2 is a problem. We can't go to 2, but as we go to 2, so here's our x equals 2 vertical asymptote. As we get to, say, 2.00 from the right, 2.00001, we get 1 over 0.00001, which is perhaps 10,000 or 1,000, however many zeros I said in there. It's getting bigger and bigger and bigger and bigger. If I put in 1.999, I get 1 over negative 0.0001, which is perhaps 1 over 1,000, but negative. So this is a graph that wants to approach that vertical asymptote in that manner. So it's getting very, very steep. If I put in just a tiniest bit over 2, we're basically approaching infinity here. So that's our vertical asymptote, and we have horizontal asymptotes that perhaps, and this is all based on what I refer to as the big X test. As you can see, if I put a huge positive value in here, I get 1 divided by a huge positive value, which is trying to be 0, but it's still positive divided by positive. Eventually this graph is coming into this horizontal asymptote. 0. If I put in a huge negative, I get 1 over a huge negative number, and 1 over a huge negative number is trying to be 0, but it's positive divided by negative, so we're approaching in this manner. So that gives us some guidelines what perhaps our graph might end up looking like, something in that ballpark. Okay, so the graph of f, the graph of a rational function, has vertical asymptotes when the denominator is 0. Well, that makes sense because we can't divide by 0. It has at most 1 horizontal asymptote, and there'll be a whole lot more discussion, and this is probably worth reading through, but I'm going to come back and I'm going to discuss big X test. So first we're going to start just trying to identify some graphs with rational functions, and the first thought might be, hey, let's just see when the denominator is 0. For instance, number 11, x plus 2 is 0 when x is negative 2, so we recognize x may not be negative 2. And we take a look. Here's a graph that it seems like we've got an issue at negative 2, perhaps a vertical asymptote. And no other graph has that issue. So 11 must be A. Number 12, here we have a vertical asymptote when x is 3 because x may not be 3. And we look around 1, 2, 3. Nope, 3 exists here. 1, 2, 3. Oh, it looks like 3 here might be a vertical asymptote, and that's the only one. So looks like D. Now, if you notice 13 and 14, x may not be 0, because then we'd be dividing by 0. So we're going to have two graphs, C and E, where there's vertical asymptotes at 0. There's problems. So which is which? Well, here's something you can do, and this is the beginning of the discussion of the big X test, which causes some challenges for people, but you guys are the best of the best. When I put in a big positive value for x, let's say 1,000,000, I get 4,000,000 plus 1, big deal. I would suggest that plus 1 really doesn't have a bearing when x gets big. Now, when x is little, then the 1 is important, but when x is a billion or a trillion, that 1 doesn't matter, and the numerator just wants to be 4x. The denominator wants to be like x, and 4 divided by x is 4. I mean, just by time I put in 100, I get 401 on top over 100, which is basically 4. We're getting pulled into 4. So we're looking for a horizontal asymptote at 4 and a vertical, so we want a horizontal y equals 4. So here is y equals 4. Looks like what that graph pretty quickly tries to take on the value of 4 to the right and left. Whereas number 14, when x gets huge, let's say I put in 100, I'd end up with negative 99 on positive 100. That's just about negative 1. And there's our other graph right here. If I look at negative 1, looks like we have an asymptote at y equals negative 1. Negative 99, I don't know why I put that there. Okay, so let's take a look. X may not be 4, which leads me to believe, let's see, 1, 2, 3, 4, that's a possibility. And I think that's that's negative 4. 1, 2, 3, 4. It looks like B is a possibility here. Let me go back and answer 13 and 14 then. I'm sorry. 13 we decided was C. 14 we decided was E. X may not be 4, but now hopefully we understand we can kind of confirm that horizontal asymptote as well. As X gets huge, let's say 100, we would get to 92 over 96. Nope, 98 over 96, which is just about equal to 1. And so we see here, not only do we have the vertical asymptote, looks like there's a horizontal asymptote. It's trying to be 1. It just never quite is because it's offset. So this is B. So here I'm going to distribute this and make it negative x minus 2 on x plus 4. Distribute that negative. First off, we recognize x may not be negative 4, which implies only graph F. But if x is huge, the 2 and the 4, is what I refer to as the big X test, cease to become very significant, and I get negative x on x. It wants to look like negative 1, and sure enough, there's negative 1, y equals negative 1, x equals negative 4 for F. Okay. Let's continue down this road as I scramble to see where I left the rest of my notes for that section. Okay. Continuing on, finding vertical and horizontal asymptotes. Then if we understood that last section, we should be in pretty good shape here. Find any asymptote of the graph of the rational function. So we know that x minus 2 cubed may not be 0, so x may not be 2. And if I was graphing this, that means 2, x equals 2, is a vertical asymptote. We can't touch that graph. Vertical, a little easier to find than horizontal. Okay, if I was to FOIL this out, I would get 3 on x cubed ... As I put in huge values for x, the numerator just stays 3. Like if I just put in 100 here for x, when x equals 100, this would be 1 with 6 zeros. This would be 1. This would be a million. I'd be on a million and then some other. So 3 divided by a huge number is going to approach 0. It's going to end up looking like this. When I put in a huge negative number, a negative to the third becomes a huge negative. I get positive divided by huge negative. 3 apples to feed the world. Everybody gets nothing, but positive divided by negative is negative. It wants to be this way. So our horizontal asymptote is y, the height, wants to be 0 eventually. It just never quite gets there. Okay, 20. When x gets huge, like if x is a million, we think this is a big deal because we'd have 4 times a million. Sounds big, but this is a million millions minus just 4 millions. So it's still almost a million millions over a million millions. This 4x and the negative 4 cease to become real big players in this, and therefore the graph wants to look like x squared on x squared. The graph wants to look like x squared divided by x squared 1. It just never quite is because we're offset. And we recognize that x squared minus 4 may not be 0. So let's check. When x plus 2 times x minus 2 is 0, that means x equals negative 2, x equals 2. Those are our horizontal asymptotes, and as we said, our vertical asymptote is y equals 1. Okay. All right. Find any asymptotes and holes in the graph of a rational function. So holes in graphs occur. You'll have a graph that might look something like this. And then you go and you look at, oh, what is f of negative 2? And you check it on your calculator, and it looks like it should be 1, and it tells you it's nothing. Sometimes holes appear in graphs. And holes appear in graphs when there's common factors in the numerator and denominator that cancel. So let's take a look here. This factors into x plus 1 squared, or x plus 1 times x plus 1. This factors of negative 6 that add up to be negative 1 are negative 3 and positive 2. This factors into, if I make this outside product be 2x, biggest factor 2x and 1. First times first equals first, x. Last times last equals last, minus 3. So here's what we would note. If I didn't know the numerator, I'd say, well, we have zeros of 3 halves and negative 1. But we have a 0 up here, a double 0 at negative 1 as well. If we cancel this, that is a dead giveaway. We have a hole at x equals negative 1. When we cancel a factor, numerator, denominator, the graph will look like it's continuous there, but there's just a tiny little pinprick hole. Okay, so after that, we take a look at the denominator, the rest of the denominator. 2x minus 3 may not be 0, so x equals 3 halves is a horizontal asymptote. And for vertical asymptotes, the graph of this ultimately, when we choose big values for x, wants to be x squared on 2x squared. Cancel the x squared, the graph wants to look like 1/2, but it never quite does. So y wants to be 1/2 is our, vertical asymptote here. Vertical asymptote, x equals 3 halves, y equals 1/2 wants to be our horizontal asymptote. So find any asymptotes, got them, any holes in the graph, verify your answers. Highly encourage you take a look at that. And the verification. Okay, number 24. I'm going to rewrite this as negative 5x squared minus 14x plus 3 on 2x squared plus 7x plus 2x plus 3, and then I'm going to factor the negative out of the numerator. So I'm just going to make this the opposite of 5x squared be plus 14x and would be minus 3 all on 2x squared plus 7x plus 3. And now we're going to try to factor. So this is the opposite. I would have to have a 5x and an x. And let's see, I think I need positive. I think I'm going to have a plus 3 and a minus 1 there. 15x minus an x. Got it. There's my minus 3. And factors of 6 that add up to 7 are 6 and 1. So I'm going to have an outside product be 6 by doing this. And you can factor this your own way. Here's x, here's plus 1. You can take a quick check and see that we have it. Therefore, here's our cancellation. The graph wants to look exactly like y equals this, except there'll be a hole at negative 3. So we have a hole at x equals negative 3. That's a big study in calculus, how we handle that. I should be zoomed in here a little bit for you. Vertical asymptote is when 2x plus 1 equals 0, or x equals negative 1/2, because 2x plus 1 can't be 0. We don't say there's a vertical asymptote at x equals negative 3. That's the hole in the graph. And then in the big picture, if we look at this, negative 5x squared and 2x squared become the dominant terms of this rational function. And therefore, the graph eventually just wants to look like this on this. The x squareds cancel, and our horizontal asymptote becomes negative 5/2. X squareds cancel. It never quite gets there because it's offset a bit. Okay, 26. In 25 through 28, find the domain of the function. Let's start with that. A, the domain. Here's what I know. X squared plus x plus 9 cannot equal 0, so let's see when it is 0. Well, there are no factors of 9 that add up to 1, so opposite of b, negative 1 plus or minus square root b squared, that would be 1 minus 4 times a times c, 4 times 1 times 9, 36, and I'm done right there, all on 2a. I recognize x is never going to be 0. Or excuse me, x squared plus x plus 9 is never going to be 0. Therefore, there are no bad values to choose here. A quick look at that graph, we would notice that it starts up 9, and it wants to go, it starts up 9, it's rising through there, not real fast, and then it wants to look like a positive parabola. Yeah, it doesn't really come very close to the x-axis. We don't get any zeros there. So find the domain. I can put in any number I want. So the domain is all real numbers. B, decide whether the function is continuous. Well, because I can put in any numbers for x I want, B, it is continuous. And C, identify horizontal and vertical asymptotes. Horizontal asymptote, what does this graph want to look like eventually? That's when we look at our lead terms. 3x squared over x squared dominate the top and bottom. Eventually it'll look like that. X squared cancels, so the horizontal asymptote would be y equals 3. Vertical asymptotes, there are none because we can't make the denominator be 0. And I would highly encourage, verify your answers graphically. Let's take a look at 28. So A, find the domain. We know that 3x cubed plus 24 may not equal 0, so let's see when it is 0. That's when x cubed equals negative 24 divided by 3, negative 8, and that is when x equals the third root of negative 8, or x equals negative 2 is our vertical asymptote. Any other value for x is fine. I'll go with B over here. Decide whether the function is continuous. It is not continuous because we'd have to pick up the pencil at negative 2. And perhaps there's a hole in the graph there. I'm not certain there is, but perhaps there'd be a hole in the graph there, but x may not be negative 2. Actually, do we know that's a vertical asymptote? Yeah, I think we'd have challenges trying to factor this. We could put negative 2 in here. We get negative 8, negative 32. Yep, it's negative 2 is not a 0 of the numerator, so it's a vertical asymptote. C, here's our find the domain. Oh, so our domain in A, is x may not equal negative 2, and that's it. C asks for vertical horizontal, so vertical asymptote, x equals negative 2. Horizontal asymptote, what happens when x gets big? This becomes pretty easy for us after a while. only looking at the biggest exponents, top and bottom, they cancel and we end up with 4/3. The graph wants to eventually look like y equals 4/3, but it may look crazy for a little bit toward the middle of the graph or towards 0 until we get out for big values of x. And then we're to maybe take a look at our graph. All right, continuing on. Determine the value that the function of f approaches as the magnitude of x increases. So we get big values of x. If f of x is greater than or less than this value when x, or is f of x greater than or less than. So we're just going to consider what happens as x gets really, really big. As I put a big positive in here, like even just 100, I would get 2 plus 1 over 97. If I put 1,000, 2 plus 1 over 997. This value gets closer and closer to 0, but never gets there. So this is a little bit more than 0, plus 2, a little bit more than 2. The graph wants to, as I put big positive values, get closer and closer and closer to 2, because this part gets closer and closer and closer to 0. As I put in a big negative, so this would be to the right, this would be as we go to the left. I put in a big negative like negative 100, I get 2 plus 1 over negative 103. This is 2 minus just a little bit. So the graph here wants to look like that, a little bit less than 2 as we move out. Gets closer and closer to 2 as we move that way. Gets closer and closer to 2, but 1 from above, 1 from below. So determine the value that the function approaches as the magnitude of x increases. The function approaches 2. That's the y value. Is the function greater than or less than this value? For large x, it's a little bit above. Greater than 2. For, we'll go large negative x value, it would be slightly less than 2. Okay. 36. Think about it just for a minute here. As x gets really, really, really big, the graph wants to look like 2x over x squared. That's 2 over x, so it wants to look like 2 on x. And if x is big, a billion, 2 divided by a billion, 2 apples to feed the world, everybody gets nothing. This graph wants to get pulled into 0. When x is big and positive, out to the right, so in this case, the function approaches 0 to the left and right. As we approach to the right, or as we get big positives to the right, we get positive divided by positive is positive, so it must be above 0. We get greater than 0. As we move to the left, we get negative. A big negative, negative 100 would make this a negative numerator, but negative gets absorbed here. I get negative over positive, which is negative, and it wants to approach from below, from less than 0. It's possible we could have functions like this that are both above the horizontal asymptote. Okay, and in exercise 37 to 44, find the zeros, if any. Well, the function, we get zeros if the numerator is 0, like 0 on 7 equals 0. 0 on negative 9 equals 0. 0 on 0 equals, that's a story for a whole nother day, and that's just about the whole reason that calculus came about. And we'll be talking about that in class, but 0 on 0 would be a problem. So I want to know, when is x cubed plus 8 equal to 0? And there we had this in class the other day. That's a perfect cube plus a perfect cube. We could actually factor that, but we could also just do this. When is x cubed equal negative 8? When x equals third root of negative 8, when x equals -2, the numerator is 0. Does -2 make the denominator 0? No. Therefore, find the zeros if any of the rational function. There's our only 0. And again, I would encourage that till you're really comfortable with the algebra. Okay, in this case, we're trying to find the zeros. If I set 3 minus, in fact, I'm just going to make that 3 plus 12 on x squared plus 2 equals 0. We'll solve this for x squared, or just for x. I'm going to subtract 3. I get 12 on x squared plus 2 equals -3. I get cross multiply. 12 equals -3x squared minus 6. I'm going to group everything on one. Nope, no I'm not. I'm going to keep my x squared. Let's see, I'm going to add 3x squared this side. 3x squared equals, subtract 12, -18 onto that side, and I get x squared equals -6, which may not happen. Therefore, we don't have any zeros of this function. We can't be 0. If we look at it this way and think about it, well, what do we have? We have 3, so the graph wants to be up 3, and whatever x is going to be positive, plus 2 is positive, so my graph is always 3 plus 12 on a positive number, and 12 on a positive number is positive. We have no zeros here. There are none. And finally, 44. I'm going to factor. Let's see. I think I can get this one, 2x, and factor on your own, but there's a 10, and I can get an 11 here, 2x and x plus 1. Okay, now, part of me suspects maybe one of these things is a factor, but I'm just going to sidebar this. We'll go 3x squared plus 13x minus 10. Factors of -30 that add up to be 13 would be positive 15 and -2. I'm going to choose outside factors of -2x. Excuse me. Biggest factor of 3 that divides into 2 is 1x, so I need a -2 here. X first times first equals first, 3x. Last times last equals last, -2 times plus 5, and there's my missing 15. So this is 3x minus 2 and x plus 5. So we're supposed to find the zeros. Well, I can't put -5 into this function because it would wipe out the function in the denominator. The first thought would be, hey, the zeros would be when this equals 0 or when this equals 0, but this is part of a whole, not a 0. So my only 0 occurs at 2x when 2x plus 1 is 0, or when x is -1/2. Common mistake would be to say and -5, but -5 is not a 0. It's the location of a hole in the graph. I would highly encourage you to graph this and then do second calc value -5. And you would see that it would be x equals -5, and then off to the side you'd have y equals, and it would just leave it blank. Okay, that is 2.6. It's part of the bigger picture. 2.6 and 2.7 go together. We do not want to have any questions lingering as we move into 2.7 about any of the material we covered here. So let's make certain we're double checking homework, we're verifying on graphing calculators unless we're 100% certain that we're on track. And here's your assignment. Good luck, and let's make certain we're asking questions.